Debugging is the process of finding the mistakes in your program when it crashes or fails a test. Debugging is hard. So the first rule of debugging is to use good practices so that you don't have to debug. One of those such practices is to use iterative enhancement. Another is to break a problem into subproblems. A third is to keep patterns in mind. And the fourth is to maintain intellectual control of your program. In the rest of this video, I'll go over these one by one. First, iterative enhancement. That means to repeat the following. You find a stage for your problem, and you solve that stage and test that you've solved it correctly. And you find another stage, solve that one, testing it. Third stage, solve that one and testing it. And you keep doing that, making steps toward a solution where each step is a small step and can be tested. That's the key. At each stage, you test the stage and get it working before you go on to the next. Here's an example from your Session 7 problem where you were to draw n lines. Each one was to be vertical with length 50. The top of the first was at a given point. Subsequent one was to be 20 pixels to the right and 10 pixels down from the previous. The first one was supposed to have thickness 1, every one after that 2 greater thickness, but no greater than 13. And you would return the sum of all the thicknesses. Go ahead and pause the video now while you think about what would be an iterative enhancement plan for this problem. That is, what would be a series of stages that you could use to solve this problem. Let's pause the video and think a little bit about that. So here's one possibility. Remember, the problem we're trying to solve is to get the lines to be drawn like that. A bunch of them in a sort of downward right thing with increasing thicknesses. So one plan would be to first get your test window to show up, and perhaps you would draw your test point and later remove that point, but it's there for purposes of testing the next stages. The second stage might be to draw just the first line at the right place. The third stage might be to draw all n lines, still thin though, no thicknesses yet. The next stage might be to get thicknesses involved, having them grow by 2 per line, and the stage after that to halt that growth at 13. The final stage in this plan would be to test that the returned value is correctly, get the returned value to work and test that. So that is an iterative enhancement plan. I can't emphasize too strongly how critical it is that you use iterative enhancement on every problem that you do. Every problem can have at least a few stages, and you'll find that you'll have much better success finding the mistakes in your program if you work in small stages where you know for each stage just what code you've added and therefore just what code is probably causing the mistake. The second of these practices to help avoid debugging is to break a problem into subproblems and write and test separate functions for the subproblems. This hasn't been too much of this. You haven't used this You have not had need to use this technique much so far because your functions have been small. But as you write larger and larger programs, you'll find this to be more and more valuable. Here's an example. In one of the problems, you were to given a list of subsequences, and you were to return a list that contains only the subsequences that contain only integers. For example, if the given argument is listed, you'd go through, you'd look at 314, only integers, keep it. 10 high, 10, no, it's got high, throw it away. 125, no, it's got 2.5, not an integer, throw it away. Hello, doesn't have integers, it's a string. The empty list doesn't have any non-integers in, so you keep it. The string 404, no, that's not an integer, throw it away. 30 minus 4, yeah, keep that one. So this function is to return the list of those 3 elements that it's pointing to. So take a moment and figure out what would be a reasonable subproblem for this problem. What would be a reasonable subproblem that you might make into a function of its own? Pause the video and give that some thought, and then continue after you've thought about it a bit. So remember that we're doing that keep integers problem that has a list of lists trying to keep the subsequences that contain only integers. So one way to solve that problem is to loop through the list as we just did in our example, and for each subsequence, determine if the subsequence has any non-integers in it. That latter part, written in blue there, could become its own function because it's not trivial to determine if a subsequence has any non-integers in it. So in this way of solving the problem, what you would do is write a helper function, that's what they're called, that checks that given a sequence, sees whether all the things in there are integers. That would be using the find pattern as written there, that you look through, go through your sequence. If the type of something is not an int, well, then it doesn't contain all integers. If you get all the way through, then it does contain all integers. And then your actual keep integers function would go through the outer list of sequences, calling the helper function you just wrote is all integers. If the helper function applied to the sublist is true, then you would append that sublist to your answer, and you'd build up the answer and return it. So this is a good example of a sub-problem that was worthy of having its own function, and you should feel free to make such functions in any problems that you encounter. In the problems we've done so far, it's mostly loops within loops that this would be helpful for, but again, as you get to larger problems, you'll do this all the time. The third of the practices for helping to avoid debugging is to keep patterns in mind. So we've talked about a lot of patterns. On the left are some of those we saw before test 1. On the right are some of those we've seen since. We've seen the swap pattern, where you is written there, using an auxiliary variable to help out with the for or while loop. We've seen the wait until event pattern. We've seen accumulating a sequence, as in the example just done. And we've seen a whole bunch of patterns for iterating through sequences, including the count sum, the find, the max min, look two places at once, and looking at two sequences in parallel. And then finally, we've looked at mutating a list or object. So these are some of the patterns we've seen. When you look at a problem, one of the things you should do is try to see whether it fits in one of these patterns that you're familiar with. And if so, then that will help you organize your thoughts to write a solution. And of course, you can always look back at the patterns. Many of them are from session 11 to remind yourself how they work. The fourth and last of the ones I'll talk about of the good practices to help you avoid debugging is to maintain intellectual control of your program. Now that's a hard thing to do with lots to it, but the simplest part of it, just the least part of it, is to use descriptive names, use sparse but well-chosen internal comments, and use white space well. For example, in this code shown right here, the index of largest number function, in terms of names, well, you should use plurals for names of sequences. So numbers for a sequence of numbers. Almost all lists or other forms of sequences should have a name that ends with an S, a plural. You should use singular for non-sequence items like a circle or circle 1. Second, the name might indicate the type of object. So index of largest, that variable here, that name, is to be an index, something you put inside the square brackets. The name makes that plain. That's not enough, though. The name should always indicate what it stands for. So index of largest, it's the index of the largest number you've found so far. Similarly, you would use, instead of just point, if you're doing a thing with rectangles, you'd write upper left corner if that's the point you're talking about. Again, the more descriptive the name can be, the better. You don't want terribly long names. That just makes them hard to read. But within reason, descriptive names. Now, some names, like an index variable of a loop, there is no particularly descriptive name, and so we fall back to tradition that goes back over 60 years in the language Fortran, where such names were required. And we use letters like J, K, I, J, K for looping variable for the loop variables, for the index, for the variable that goes in a loop. And finally, if we have a name that is an integer but doesn't have any other particular meaning, it's just some integer, we typically use m or n for that, and maybe we use x or something like that for a float that has no further meaning. So those are some of the uses of names that help you keep control of what your program is supposed to do. The name makes it clearer to you as well as to other readers what this program is doing. Additionally, you should occasionally, not always, not even often, but occasionally have some internal comments that clue you and the reader to what's going on. So this one is using the traditional max-min pattern, so I put a little comment there saying so. You should not clutter with too many of these. Code should generally be self-documenting, but a little comment, carefully chosen here and there, can help to help you and others keep intellectual control of your program. And then finally, white space. You should separate the chunks of a function with a single blank line. Not more, because it makes it harder to read. Not less, because the blank line chunkifies things. It shows the logical chunks. The standard for function definitions is to have 2 blank lines between them. So, to review, you should always use iterative enhancement. I can't emphasize that too strongly, that you find a stage, get that stage working. Find another stage that's getting closer to your solution, get that stage working. It's critical that at each stage you can test whether it's working. Similarly, you might want to break a problem into subproblems and write and test these helper functions for the subproblems. You should keep your patterns in mind, and you want to maintain intellectual control of your program for sure, and some of the techniques to do so include using descriptive names. Use these practices to minimize the need for debugging. Subsequent videos will show you how to debug when you have to do so.